Hi folks, we're going to take a look at page 257, number 12, which was also a question on the lesson sheet. So let's take a look what they're asking. So it's saying an irrigation channel is to be constructed by bending a sheet of metal that is 3 meters wide. What angle theta will maximize the cross-sectional area and thus the capacity of the channel. Okay, so let's think about what we're doing here is we're taking a piece of metal and we're bending it essentially into the shape of a trapezoid, and that's creating a volume that, say, water can go through. And since it's a prism, what is going to give us the biggest volume is to get the biggest area of the base. So if we can maximize the area of the base, we'll maximize the amount of water that can go through that channel. All right. So let's take a look at how we can do that. So first of all, I'm looking to maximize the area of a trapezoid. So that gives me the model with which I'm going to work with. So the area of a trapezoid is the sum of the smaller base plus the larger base times the height divided by 2. All right, let's just recall what that is. So we have our smaller base, which is just this length here. So that's just going to be A, which we already know is equal to 1. And then we've got the larger base up here, which I'll call B, and now we're going to need to find a way to come up with an expression for B, and of course we have the height of the trapezoid. Okay, now notice here that they're specifically telling us to determine the angle that's going to maximize the area. So that should give us a sense as to how we're going to write this model in terms of one variable. So I actually have 3 unknowns here, but of course I don't, because A is actually equal to 1, so that's fixed, whereas B and H can vary. So clearly I'm going to have to find a way to write this in terms of one variable. All right, so let's see how we can do that. So I notice here with H, I've got a right angle triangle, so that'll be helpful in terms of writing H in terms of theta. So here I see H is the opposite. 1 is the hypotenuse, so I can use sine of theta is equal to H over 1, or H is just equal to sine theta. So I've managed to write the height in terms of theta, so that's good. So now the question is how I'm going to write B, hopefully also in terms of theta. Well, here what I'm going to do is I'm going to take this length B, and if I draw 2 lines here, okay, well, that's just equal to 1, and then these 2 portions are the same because it's an isosceles trapezoid, and I see that this length here is exactly the adjacent side to that triangle that I already worked with. All right, and so from here, let's say I call this X, I'll be able to use cosine to write X in terms of theta, because I have cosine of theta is equal to the adjacent X over the hypotenuse, which again is 1, and so X is just equal to cos theta. All right, and so what I have now here is a way to write these 2 variables in terms of theta, because now B will just be equal to 1 plus a cos theta here, another cos theta there, so 1 plus 2 cos theta. All right, so let's put this into our model here. So we've got A now can be written as A was just equal to 1 plus B we said was just equal to 1 plus 2 cos theta times the height, which is just sine theta, all over 2. All right, and what we have now is a model for the area of this trapezoid given in terms of one variable, and not just one variable, but the one we're actually interested in studying. All right, so let's figure out what the domain is. Okay, well, I see that theta is the angle from the horizontal there, so we can see that theta can't actually be equal to 0, otherwise we don't have a channel that's created. So theta definitely has to be bigger than 0. Okay, so we can see that we're not going to have a closed interval. And I think we can assume that theta has to be less than or equal to 90 degrees. It doesn't make sense. Well, sorry, let's see if I can get this. Doesn't make sense to create a channel where theta is bigger than 90 degrees. Okay, or pi over 2 radians. Because of course, if we want to use calculus, we're going to want to work with these trig ratios in radians. All right, so I'm going to say here that theta has to be bigger than 0, but less than or equal to pi over 2. Okay, so in the end, this is not a closed interval, so I will have to justify any optimal values that I find. Okay, so let's clean this up a little here. So we get A is equal to 2 plus 2 cos theta times sine theta over 2. I'll factor out the 2. So 2, 1 plus cos theta times sine theta. So there goes the 2's. And then finally here, I'll just distribute that out. So that's going to be sine theta plus sine theta cos theta. All right. And I just realized here that if I had kept the 2 there, I could have replaced 2 sine theta cos theta by sine of 2 theta. But in the end, I kind of prefer getting rid of that 2 in the denominator. If I don't have to carry on the fractions, I'm happy to do that. And this is going to be a pretty easy derivative to take. All right, so let's now go and do the calculus now that we have our model in terms of one variable. So here the derivative of sine theta is just cos theta. And then here I'm going to have to use the product rule because I'm multiplying sine and cos. So I have the derivative sine, which is cos, times cos. So I just have cos squared theta. And then here I've got sine theta and then times the derivative of cos theta, which is negative sine theta. So let's clean that up here. What do we have? We have, looks like cos theta plus cos squared theta minus sine squared theta. All right. And this is where I run into a little bit of a problem because obviously I want to figure out when this is equal to 0. I want to look for my critical points. But I'm not quite sure how I would solve this equation as is, okay? And the problem here is this sine squared when everything else is in terms of cosine. So this is where hopefully you remember that this should look very familiar. That cos squared minus sine squared is just one of the 3 double angle formulas for cosine. So this is just cos theta plus cos of 2 theta. Okay, that these two are equivalent, so making use of our trig identities. Now again, here, I'm not sure how I would solve this, but we remember that cos of 2 theta has 2 other versions of it, and one of those versions contains only cosine. So let's see what happens if we use that other identity. So cos 2 theta can also be written as 2 cos squared theta minus 1. And now this is starting to look more promising because this looks a lot like a quadratic trigonometric equation. Okay, so let me just clean it up here. 2 cos squared theta plus cos theta minus 1. And even better than that, looks like this is factorable. Okay, so 2 cos theta and then here cos theta. So this has to be 1 and 1, and I need a positive 1, so this is going to be plus 2 minus 1. All right, so looking good so far. We've got everything working out as we hope, because not only were we able to write this in terms of one variable, we also get something that we can solve fairly easily. So here we have cos of theta can be equal to 1/2, or cos of theta is equal to negative 1. All right. So now we're only working between 0 and, oops, let me show you that there. We're only working between 0 and pi over 2. So the first thing I notice is that cosine theta is never equal to negative 1 in that interval. Okay, so here, no solution in 0 pi over 2. Okay, because cosine of theta is equal to negative 1 at negative pi, which is not in my interval. So no solution there. So now we have to remember, well, when is cos theta equal to 1/2? All right, so here we've got, you can use your old special triangles here. So it's going to be when the adjacent is the smaller one, so 1/2, and that happens when theta is equal to pi over 3. Okay, and that is in our domain. Okay, so we have this one critical point. We just have to show that this represents a maximum in this domain. All right, so let's test a prime. Okay, so from 0 to pi over 2, and we're testing out, oops, sorry, pi over 3. Okay, so let's figure out the best way to do this. So I guess we can use something. Actually, you know what? I'm gonna cheat here and just use my calculator. I was gonna do this by hand, but you know what? I don't feel like calculating these. All right, so let's pick something smaller. So pi over 3. So pi is about 3.14. So let's say we take, I don't know, 0.2. All right, so let's stick that into our expression for the derivative of the area. Make sure you're in radians. So what do we have? We have cos of 0.2 plus cos of 2 times 0.2, so 0.4. And we get something that is positive, so that's a good start. And now let's pick something that's between these two here. So here pi over 2 is about 1.57, so let's pick 1.5. All right, so here we've got cos of 1.5. Okay, and then it's plus cos of 2 times 1.5, so cos of 3. And we have a negative number there. All right, so given that this is the only critical point in this interval, so this here tells me that it's a local maximum because the derivative is 0, and I'm going from positive to negative on my derivative, but I see that I'm always increasing from 0 to pi over 3, and then always decreasing as I'm going from pi over 3 to pi over 2. So this justifies that this is not just a local maximum, but in this interval, it's an absolute maximum. All right, so let's go back and read what they're actually asking us for. And here it says what angle will maximize the cross-sectional area. Okay, so they're not asking about the dimensions of B and H. They're not asking for the area itself. They're asking just for the angle theta, which is what we've already found. So no other work to do. So here our answer is pi over 3. All right, so let's just do a quick recap. So step number 1 was to realize that we were working with the area of a trapezoid. Step number 2 was to find a way to write the variables in that formula in terms of this angle theta, which we were able to do using just some simple trigonometry. And then from there, we went through our calculus tools in the process using a couple of trig identities to eventually get to our answer of pi over 3. All right, that's it for this one.